Okay, so this is the kind of application you're going to see in this section on rational equations. So this is what's called a classic working together problem. Anytime you do a working together problem, as soon as you realize that things are working together to accomplish a task or to complete a job, you want to approach it the same way. So I'm going to show you how to approach that. I'm going to show you two different ways to approach it. One of them is like the easy way to remember and set it up and just get the answer, you know? But before we get to that part, I'm going to kind of show you a way that I think makes a little bit more sense, hopefully. Either one is completely doable. One of them, as soon as I see it's a working together problem, I just go for that. And it's pretty easy to do, you'll see. Okay, so we've got Brenna. They're making cookie cutter apartments. My inspiration for this problem was my brother-in-law visited China this past summer on a music tour. He's getting his PhD in percussion. And while he was doing that, he encountered what are called ghost towns in China. Because in China, there's currently like 10 to 20 cities that they've built for like 2 to 3 million people that are completely empty. They are just building and building and building, and it's starting to have an effect on the Chinese economy. This might not be the only problem associated with that, but they're just completely empty, and they just keep constructing these apartments, and not enough people can really afford them. So it's kind of maybe a future planning thing, or it's a gross domestic product inflation thing. It's complex economics. But anyway, this kind of thing happens a lot. So Brenda's building these cookie cutter apartments with her friend Joe. He's more experienced. She can do it in 16 hours. We don't know how fast he can do it. That's the thing we're trying to find. But together they can do it a lot faster, of course, because, you know, one of them's feeding lumber, the other one's cutting wood and all that kind of thing. So together they can do it in 4 hours. So I want to figure out how fast is Cho if he's working by himself. So clearly this is a working together problem. It doesn't have to be people working together, though. You're going to see a problem where like 2 pipes are filling up a tank, and hence the pipes are working together to fill it up, you know what I mean? There's also the situation of you have 2 batteries trying to charge a circuit or charge a capacitor in electronics. So it's a really common situation, okay, when things are working together. And it doesn't have to be just 2 things working together. It could be more than that, but we'll stick to mainly 2 things, all right? So how do you do this? I think you want to focus on the idea of completing a job. So I'm going to say something is equal to 1 complete job. So I'm going to open by explaining how this works kind of theoretically. Let's see if you guys get it. So in order to complete a job, 2 people are performing the task, right? So I think we're going to have 1 part's contribution plus the other person's or part's contribution. So I think the idea here is we want to think about how fast Brenna's working, Brenna's rate, in other words, how fast she's doing the work. We want to think about how fast Cho is doing the work. And in order to get a complete job, what are we going to have to multiply their rates by? Yeah, like the 4, like the how long they're doing it, exactly, you got it. So this is like times how long and times how long. So this equation right here, was a pretty simple little equation, represents when they're working together or separately? When they're working together, right? So Jensen already told me the how long part in both parts is going to be what? 4 on this one. Great. So for us, we're going to have 4s here. So the part that might be a little bit trickier, that's just 1 over there for 1 complete job, 1 complete apartment unit. The part that might be a slightly trickier is, what is Brenna's rate of accomplishing work? Yeah, it takes her 16 hours to do the whole job, but what's her rate per hour? She gets 1/16 of the complete job done every hour when she's just working alone. That's her rate of work, okay? So we don't know Cho's rate of work, so how should I write it then? He gets, it's a reciprocal, 1 over his rate, because we're looking for that. And then this 4, of course, is their working together thing. So that's kind of the theory. If you look at that a little bit more carefully, review it one more time, go through my explanation on the video or look at the book or whatever, it does totally make sense. But it's a little bit hard to put together from memory, you know what I'm saying? So when I put this together from memory, I just remember this. So this is the theory way. What's the practical way, like I would have wanted in high school? The practical way is to think of this as a reciprocal equation. It's just a reciprocal equation, because what can you do to this equation if you want to with that 4? So there's a reciprocal here, there's a reciprocal here, there's not one over here. But see, there's a 4 multiplied on both spots here. What could you do with it if you wanted to? You could divide that whole side by 4, and then it would cancel these 4s and move that 4 underneath over here. So an exact equivalent to this problem is 1/16 plus 1 over x equals 1 over 4, if you divide both sides by 4. That is so much easier to remember. All you have to do to work a working together problem, as soon as you realize there's stuff working together, remember, oh yeah, working together stuff is a reciprocal equation. So I put 1 over the rate of work for the first piece, or person, plus 1 over the rate of work for the second piece, or person, equals 1 over the rate of work for the total, the combination of those people. If there's 3 things working together, it works the same way. That's really easy to remember, and then you just solve it. Does that make sense, guys? So why does this work? The y isn't up here. But you can just do this and get the job done. So it's a rational equation, right? So can you guys help me solve it from yesterday? These aren't bad. I multiply by the, I want to chop off fractions. You guys remember killing fractions?
Just do x. That works.
I need the least common denominator. It needs an x, you're right. What else does it need?
6.
Kill stuff. Well, it needs a 4 at least. But if I just put 16, doesn't 16 have a 4 built into it already?
Yeah.
If I just put 4x, that wouldn't quite kill this 16, right? So you got to think of something like that. Now, is 16x the only thing you could multiply by to kill stuff? No. You could use like what? 64x, that would work. 32x would work. Totally, any of those things would work. So let's multiply through by it, and fractions will be gone. So 16x, 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 multiplied, right? Cancel out what cancels. X is left there, 16 is left there. 16 over 4 is 4, and an x. It's just a little linear equation this time. So solving this is pretty easy, it's just a setup. So 16 equals 3x, x is 16 thirds. Let's think about this. 3 goes into 15 5 times. And then 1/3 left. Is that right? So it's like 5.33 continuing. So that's how fast Joe gets this job done. Let's write it out real quick, just so we're clear. So Joe could build an apartment, one of these kind at least, in 5 1/3 hours by himself.
He's like a machine.
Slow. This is the way framers work, though. I mean, if you got a lot of experience, you can go really fast. If you don't have as much experience, you can still do a good job. It's going to take way longer. Okay?